So last time we got to start a discussion on aromatic compounds. Give me your definition of aromatic.
Unusually stable.
Okay, things that are unusually stable. Works really pretty well, right? And there are 4 criteria. And what are those criteria? Cyclic,
Must be planar.
completely conjugated, what's that, Aubrey?
Planar.
Planar, and what?
And then that insert rule, the H word.
Whose rule?
Huckles.
Huckles.
H word. So,
Which is what?
2N.
4n plus 2 equals pi electrons. That's right. And so we determined then that things like benzene were aromatic because they satisfied all 4 criteria. You have to satisfy all 4 criteria, right? Obviously, benzene's a cycle. It's planar. It's completely conjugated, and it satisfies Huckles' rule because 4n plus 2 equals 6 if n equal 1, right? And so Huckles' rule states that that n has to be a whole number. It'd be 0, 1, 2, 3, blah, 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 right? And so we're going to continue a little bit of a discussion on this today. But before we do, I want to talk a little bit about the molecular orbitals of benzene. How many p orbitals does benzene have? It has 6 p orbitals. So how many molecular orbitals must benzene have? 6. And you need to be able to draw all those molecular orbitals and their relative energies. The cool thing is, for aromatic compounds, at least that are monocyclic, it's really, really easy. If you can draw a regular polygon and make one of the vertices point straight down, you can do it. So all you have to do for benzene, you know you're going to get 6 orbitals. You just have to draw the shape. You don't even have to draw in. And then what do we do?
Do you have to draw in fuel?
Not quite yet. What do we draw?
Do we draw in our fuel orbitals?
Nope. What'd you read? The circle method. What's it called? The frost circle. How do we do that? We've got the shape. Now we inscribe that shape inside a circle. So we draw a circle that touches all the vertices. And where that circle touches all the vertices, that's where an orbital energy is going to be. And so you're going to have an orbital here, 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 and here. So if I want to draw that without, you end up with something that looks like this. And then you bisect the circle in half, and that draws the line that you need. How many electrons do we have for benzene? How many pi electrons? 6. So what do I do in terms of filling the orbitals? How do I fill the orbitals? Pardon?
Put 1 in each.
1 in each. How do I fill orbitals? Huh? We start at the lowest energy, right? And so I put an electron in there. Now what do I do? Do I put another electron there, or do I move up? Do I move up? Think back to your Gen Chem. We're going to fill before we move to the next highest energy, right? So in this case, pairing is less energy than moving up. Okay, so we've got that orbital filled. Now what do I do? Pardon? Move on to the next one, and I put an electron there. Now what do I do? I'm going to put it in the next orbital. Why do I do it that way?
Less energy to put it next to one than this pair.
That's right. It takes no energy to put it in the next orbital. Why doesn't it take any energy to put it in the next orbital? Pardon? What do you mean by nothing there? That's true, but why doesn't it take anything for me to put the electron over there? It's not because there's nothing there in and of itself. These two orbitals are what? They're the same energy, right? They're on the same level, right? If you look at this going up in energy, right? They're called degenerate. So when we fill degenerate orbitals, we always fill until we get it half occupied, and then we go back and pair up. Because pairing requires energy, right? You have to take that electron and flip it so that it'll fit in there, right? So we do that now. We've accounted for all the electrons. And what we notice is that all of the electrons are below that dotted line. And all the orbitals are filled. That's aromaticity in terms of a molecular orbital diagram. If you have orbitals that are on this line, which is possible, those are non-bonding orbitals. You can't have electrons in non-bonding orbitals. If you have electrons in these orbitals, these are anti-bonding orbitals. You can't have electrons in anti-bonding orbitals. Now, the other day we talked about cyclopentadiene, right? And what did we say about cyclopentadiene? It's not stable, that's true, but it's more than just unstable. It's anti-aromatic. It's unusually unstable, right? I want each of you right now to use the Frost diagram to explain to me using molecular orbitals why cyclopentadiene is less stable than you would predict. So how do I do a Frost diagram for this box thing? What do I have to do to draw the Frost diagram? Well, I've got to draw the shape first. How do I draw the shape? Am I going to draw it like a box? It doesn't, because you can't do that. What's the rule? The rule is you take one of the points, the vertices, and you have to make it point straight down, right? That's the rule. And so when we do that, we get something that looks kind of like this. We draw the circle around it, right? What do we get? When we do that, we'll get an orbital here, an orbital here, here, and here. And where's my line? Now, populate the electrons. 2 on the bottom. Does that explain why it's so reactive? Why? I've got electrons in the non-bonding orbitals, and they're unpaired. So is it really a diene? What is it? No, well, there is one ene. What's the other 2 electrons, though? To be an alkene, the electrons have to be paired in the bond, right? These electrons are not paired in the bond, so what is cyclopentadiene really looking like? It looks like a diradical. It looks like a molecule that has 2 unpaired electrons. What do we know about unpaired electrons? More reactive or less reactive than paired electrons? More reactive. That's right. You will be expected on the test to use the Frost diagram to determine the energy levels of the orbitals. I will not ask you to draw the actual p orbital type molecular orbital diagrams for these aromatic molecules. Dienes, yes. But for these, I'm just interested that you know the levels.
So under the dashed line is the
Bonding,
bonding, and then on the dashed line is non-bonding.
non-bonding, and above the line is anti-bonding. Yep. It's a lot easier in Gen Chem, right? So if you remember your shapes from kindergarten and you know how to draw a circle around something, you can do this, okay? So that's all you got to do. Even if you get the shape kind of bad like I do sometimes, it still works out pretty well. Okay? All right. Today we're going to talk about heterocyclic aromatic compounds. We'll talk a little bit about aromatic compounds that pop their heads up in biochemistry. And we'll talk about why nature has chosen to use aromatic molecules in biochemistry a little bit. And then we're going to talk about electrophilic aromatic substitution reactions. It's another reaction mechanism that you're going to need to know. The fortunate thing about EAS reactions is that the mechanism is very simple. And it's the same mechanism no matter what your electrophile is. The concern for you will be remembering what reagents you need to get the electrophile you need. Okay? So we're going to talk about these three things today in the time that we have left. Pyridine is one of the more straightforward examples of an aromatic compound that has a heteroatom in it. Okay? The heteroatom obviously is nitrogen. It looks like benzene in its shape, right? How many pi electrons are there? It says 6, but wait, 2, 4, 6, 8. Right? I got 8 pairs, so why are only 6 of them pi electrons? The lone pair is perpendicular to the pi system, right? What does it mean to go from blue to red? What's this plane? That's the node, right? Where is this lying? It's lining in the node. So these electrons can't be part of the pi system. Okay? So we don't count them. This is where structure is going to be very, very important because sometimes the lone electrons actually do count in the pi system. So you got to know how the structure is, right? So there, this is just benzene where we've replaced one of the carbons and one hydrogen with a nitrogen atom and a lone pair. Okay? Pyridine kind of smells like fish. Benzene doesn't. That's because of the nitrogen. Okay? Pyridine can function as a base because of the lone pair. Okay? And we use it quite frequently for that in organic chemistry. We'll use it as a mild base. What else do I want to tell you about pyridine? Not much, actually. The orbitals look just like benzene's orbitals, and it satisfies all the rules of aromaticity.
Why did you say that is 6 pi electrons?
Okay, so if we look at it, there's the 6 p orbitals, right? Each one of them has an electron. That's where we get the 6 pi electrons. This lone pair is 90 degrees to the p orbitals, so they don't count in the pi system. They're not pi electrons. Pyrrole is another example of a aromatic system. Okay, this time the lone pair of electrons do count. Because if you look at the structure, if you built your model, you would see that the lone pair of electrons are actually in the pi system. They're in a p orbital. It's the hydrogen that's orthogonal to the plane. So how many electrons do I have? I have 2, 3, 4, 5, 6. It is cyclic. It is completely conjugated. It is planar, and it satisfies Huckel's rule. And so therefore, pyrrole is also a good example of an aromatic system. Okay? It is, comparatively speaking, unusually stable. Pyrrole, for my friends over in the polymer department, you can actually take pyrrole and you can polymerize it electrically on a surface. And it's kind of cool because it can make semiconducting polymers this way. Okay? You may learn later on about polypyrrole, and it's one of the classic aromatic systems that you can actually polymerize on a surface by shocking the heck out of it, okay? With a battery basically, and you can coat it on these conductive glass surfaces and do neat, interesting things with it. But as it stands here, it is an aromatic system. Now, if we look at other systems, we have the cycloheptatrienol system here. Notice there are 2 hydrogens. Is this aromatic? Why not? It's not completely, it is conjugated, but it's not completely conjugated. Not every atom has a p orbital, right? However, you can imagine this molecule losing a hydride, H minus. And when in doing so, now you've got a carbocation on this carbon. And the carbocation, the positive charge resides where? It is in the plane, but what's the orbital on this carbon now? What's the hybridization? It's sp2, so it has a p orbital, right? So now every atom has a p orbital. And what will happen is this molecule flattens out and it forms what's known as the tropylium ion. Okay, this 7-membered ring is known as the tropylium ion. And if we count it, there's no electrons there. 2, 4, 6. It's planar, it's cyclic, and now it's completely conjugated, and it satisfies Huckel's rule. It is aromatic. And it turns out that this molecule likes to lose hydride. Where else have we talked about hydrides before? We've talked about lithium aluminum hydride, and we've talked about sodium borohydride, and we talked about them as hydride donors. This molecule right here is also a hydride donor. It can function as a reducing agent under certain conditions. It's not very convenient to use when you have things like sodium borohydride, but nonetheless, this could work. And you're going to find out that in biochemistry, there are reducing enzymes that use a molecule known as NADPH, which we'll talk about later. Okay? It is your body's equivalent of sodium borohydride. And it gives up its hydride so readily because the product becomes aromatic. So aromaticity plays a big role in us being alive, believe it or not. Now, we can prove this through the orbitals. Drawing a 7-membered ring will take you some practice because it's not terribly easy to do. 6-membered rings we're kind of happy with. 5-membered rings we're okay with, but the 7-membered ring most people struggle with. But nonetheless, if we draw it, inscribe it in a circle, everywhere the circle touches, we get an orbital, right? And what we find is that there are 3 bonding orbitals, and how many anti-bonding orbitals? 4. And so we put the electrons in and we find that they're all below the line. It proves that the tropylium cation is in fact aromatic. Okay? Huckel's theory predicts this. Other molecules that have unusual chemistry because of aromaticity, cyclopentadiene. Cyclopentadiene has nothing more than carbons and hydrogens. It's a pure hydrocarbon. But these hydrogens are unusually acidic. What is the typical pKa value for an sp3 hybridized carbon atom? About 50, right? If you took methane and you tried to deprotonate it, pKa you'd find out would be about 50. Look what the pKa is for cyclopentadiene. 16. What is close to 16 that's not organic? Water. So sodium hydroxide can deprotonate this sp3 carbon-hydrogen bond. You can't take methane and do that. You can't take hexane and do that. You can't even take an allylic system and do that with that type of base. You have to have a stronger base to do it. But with cyclopentadiene, you can. And the reason is that we can take a base, something like, usually we wouldn't use hydroxide just because it's not very soluble, but we might use something like potassium tertbutoxide, which is soluble, right? Which has a pK of around 18. So if we had a base that had a pK of around 18 and an acid that had a pK of 16, which way would the equilibrium lie? To the right or to the left? To the right. Yeah. We always favor the weaker acid, weaker base pair, right? And so that's exactly right. So if we took tertbutoxide, mixed it with this, we would lie to the right, and we would end up with what's known as the cyclopentadiene anion. And we can draw all kinds of resonance structures for this. There's 2 more that aren't shown here. Okay? And when we take this H plus away, and we end up with this carbanion, okay, this is now aromatic. It's cyclic, it's completely conjugated, it's planar, and it satisfies Huckel's rule.
Now I know what you're saying. It's a lot more complicated than just counting.
Yep. that's amazing. 16 for a carbon-hydrogen bond that's sp3 hybridized? That's kind of cool. And it's all because the product that we get out of it, the conjugate base, right, is extraordinarily stable. Remember when we were learning in Chapter 2 about how to compare acids? We said look at the conjugate base and compare the stabilities. This is an extraordinarily stable conjugate base because it's aromatic. Okay? However, if we did the same thing with cycloheptatriene, if we had a base remove the proton, now we have a system that's what? pKa of 36. Explain that difference to me. This isn't aromatic, but it's what? It is conjugated, but if it were planar, what would it be? If it's planar, it'd be aromatic. If it was planar cyclic, it would be completely conjugated. Would it satisfy Huckel's rule? You'd have 8, so it would satisfy which rule? The anti-aromatic rule, 4n equal the number of pi electrons. So this has a pK of 36. I can deprotonate this. Will it be planar? Why not? Be more definitive than that. Don't go on the tone of my voice. Go on the facts. Will this molecule be planar? I can generate this molecule. I've got bases that are more basic than pK of 36. I can get you a base that has a pK of 50. Butyl lithium works really well. I'll mix it with this. It will deprotonate it. But will the resulting anion be planar? No. And why will it not be planar? Because if it's planar, then it becomes anti-aromatic. But if it puckers, it's just a conjugated system in certain pieces. So it'll pucker, and it won't completely conjugate. You'll have an allylic anion, like right here, and then these carbons will all kind of pucker out of the plane. And it won't completely conjugate. Because if it completely conjugates, it becomes anti-aromatic. Then it's unusually reactive. Right. Okay? So these are not unusually stable. Okay? And so this is kind of what you would expect the pK to be for allylic hydrogen, somewhere around 36 to 40. And so this just behaves like a normal allylic system. But the product will not actually flatten out and be planar, as you might expect. Now, if we take this and we remove a hydride and we get the cation, it will flatten out and become planar because then it becomes aromatic. Okay? Let's talk about some aromatic compounds that you need to know in biochemistry. This is the amino acid phenylalanine. We'll learn more about amino acids at the end of the semester. But notice that this molecule has an aromatic ring, benzene. It's got a benzene ring in its side chain. What do you all know about phenylalanine? Have you learned anything in your biology classes or maybe a nutrition class or anything? What do you know about phenylalanine? And why must it be a part of the human diet? Yeah, we can't do that. We don't have the machinery to do that. So these are essential amino acids. We got to take them in our diet. There are people, though, who have to have restricted diets for phenylalanine. They're called phenylketonurics as a class. Okay. How many of you have ever had a Diet Coke? Have you ever read the back of the can? Nope. You should read stuff that you're drinking. You should know what you're taking into your body. Huh? You could just drink water. But there's a warning on the back of your Diet Coke can for phenylketonurics because Diet Coke uses aspartame as the sweetener, which contains phenylalanine. And phenylketonurics have this thing called phenylketonuria, which means they don't have the machinery to properly process phenylalanine. They can't convert phenylalanine into tyrosine. That's one of the enzymes that we do have. Okay? And so they get a buildup of phenylalanine in their body, and it can reach toxic levels. They actually can take on a musty smell. Their skin can become actually lighter in color, and then they can die. Fortunately, they can control it with diet and some medicines and live a perfectly normal life. Okay? So if you know anybody who's a phenylketonuria, it actually turns out that they can live a perfectly normal and healthy life. They just have to watch what they eat. Okay? But an aromatic ring. Tryptophan also has an aromatic group. This whole thing here is actually aromatic. It's 2 rings, but how many pi electrons do we have? 10. Does 10 satisfy Huckel's rule? 4n plus 2 equal 10, n equal 2. That satisfies Huckel's rule. So it's cyclic, it's completely conjugated, it's planar, and it satisfies Huckel's rule. This is a aromatic ring. Okay? What do you all know about tryptophan? Probably most of you know something that's actually a myth that you've been told. You sit down at lunch on Thanksgiving Day, most of you eat a bunch of turkey, and they say it makes you sleepy. That's nonsense. Tryptophan doesn't make you sleepy, okay? If that were the case, actually, eating cheese, every time you ate cheese, you would get sleepy because cheese, by weight, has more tryptophan in it than turkey. Why do we get sleepy on Thanksgiving Day? Because we overeat, and then we sit down in our comfy chair, and we try to watch football, and we go to sleep, okay? That's why we get sleepy, not because we've eaten a bunch of tryptophan. All that stuff about sleepies and more tryptophan, it's nonsense, okay? It doesn't actually make you drowsy. There's no evidence really to support that, okay? But tryptophan is an important amino acid. It's essential. We have to get it through our diet because we can't synthesize these rings, as Aubrey said. Also, purine and pyrimidine. These are molecules that are aromatic. If we counted up all the electrons, you'd find out some of them are non-bonding, but some of them are actually in the plane. So we have 2, 4, 6, 8, 10, just like we have up here for tryptophan. We just got some more nitrogens. This is purine. This is pyrimidine. These are aromatic molecules. You will find these in DNA and RNA as bases. Why do you think Mother Nature chose to use aromatic rings to store your genetic information? Because it's stable. We can actually go find fossils and still extract DNA from it, can't we? And why can we do that? Because it's stable, right? You don't want, your DNA is your hard drive. You don't want your hard drive every time you turn it off your computer to just wipe itself out, right? Any other molecule that we could think of really to use here would have had trouble. Because organic molecules tend to oxidize in air over time. If light shined on them, they oxidize, right? All the kinds of things that I really don't want happening in my body, because if my DNA starts to get changed, I start to have mutations. I start to get things like cancer. Not healthy for me, right? However, using aromatic molecules to store my genetic information means that that genetic information will have longevity, okay? So all the things that you're learning about in terms of aromaticity, when you get up into some of your higher level biology classes and they start talking to you about genetics, you know, they're going to start telling you stuff at a very different level, but we can have genetics because of organic chemistry and aromaticity and Huckel's rule, okay? If we used other moieties, as we call them, to substitute, your genetic information would change so rapidly that life couldn't exist, okay? At least not as we know it, okay? So purine, pyrimidine, and other types of things like this are useful in storing our genetic information, okay? So I want you, this isn't a real quiz, I want you to use the polygon and circle method to predict which of the following species is aromatic, non-aromatic, or anti-aromatic. I'll add another one. Cyclopentadiene. What is it? It's going to be anti-aromatic. Cyclopropenyl cation. Own it. Aromatic, right? It is aromatic. Why do I know that that has to be aromatic? It is conjugated. It is planar. It is cyclic. And it satisfies Huckel's rules. 4n plus 2 equal number of pi electrons. How many pi electrons do we have? 2. So n has to be 0, which is allowed. Right? I know this has to be planar. Why do I know this has to be planar? Yeah, that's right. 3 points always define a plane, right? Basic geometry. 3 points define a plane. Any 3 points that I got to be in the same plane, right? How about cyclopropenyl anion? Non-aromatic? Anti-aromatic? Why do you think it's non-aromatic? And why do you think it's anti-aromatic? It doesn't do Huckel's? Are there 3 pi electrons? There's a negative charge there, right? So if this has an octet, how many electrons have to be there? Yeah, so it's got 4, right? So it's anti-aromatic. And you might be thinking, well, maybe it's not planar. It has to be, right? 3 points define a plane. So this molecule would be very, very anti-aromatic. Yes, ma'am.
Can you say that again? Electrons?
Okay, so if we look at this carbon atom, right, and it's got a negative charge on it, 2 electrons here, 2 electrons there, 2 electrons there, that's 6. To have a negative charge, it would have to have 2 electrons to satisfy that formal charge, which would give it its octet. Okay? Does that make sense? All right. So what can you tell me about cyclopropene? Is it acidic or is it basic? Cyclopropene. Yeah, that's where these came from. I can actually buy that. Is it going to be an acidic molecule or a basic molecule? It's going to be basic, and why? It is, meaning that this will lose H minus very easily, and H minus is a good base, right? So to get that, I would have to lose H minus. Right? Correct. And so cyclopropene by itself is a good hydride donor, actually. It will donate a hydride under, because it forms an aromatic cyclopropenyl cation. That's right. The cyclopropenyl cation is, by definition, the most stable aromatic, or the simplest aromatic molecule we can think of. I can't get 2 atoms to form a cycle. Okay, so 3 is the minimum. All right, let's talk about electrophilic aromatic substitution. Electrophilic aromatic substitution. What about, oh, last one? What do you think? It's aromatic. That's right. So we've already kind of talked about that one. So if we look at benzene and reacting it with a halogen like we did the other day during the demonstration, right? We know it doesn't add halogen across the double bonds. We saw that plain as day with the color, right? But I also mentioned to you that aromatic rings will undergo what's called electrophilic aromatic substitution. So if we have an electrophile, we can swap out the hydrogen for the electrophile and we can form a new electrophile carbon bond. This is known as EAS, electrophilic aromatic substitution. It's a very, very useful set of reactions, some of the most useful reactions that you'll learn in organic chemistry. So for example, we can take benzene and we can take bromine or chlorine. It doesn't work for iodine very well, nor does it work for fluorine. But chlorine and bromine works quite well. If you take benzene, let's say bromine and iron tribromide, you will form a carbon-halogen bond. The electrophile is chlorine plus and bromine plus. And notice I'm putting them in air quotes, meaning what? Yeah. Cl plus and Br plus doesn't sit around and float around in solution in these reactions. You have to have a catalyst. Notice that the catalyst X here has to be the same X that you have up here. So if you're using Br2, then it needs to be FeBr3. If you're using chlorine, Cl2, then it has to be FeCl3. Okay? The cool thing is that a lot of times organic chemists will simply put iron in the reaction instead of FeCl3 or FeBr2, because they will react with a little bit of the bromine and chlorine and form that in situ, as we say. Okay? It's a heck of a lot cheaper for me to go down to Lowe's and buy a box of iron nails, cut them up and throw a few pieces in, than it is to call up the chemical supply company and say, send me a bottle of FeCl3 or FeBr3. Okay? So I can just make it my own. So if you ever see X2 and just iron, know that that makes the catalyst. Okay? So we can make carbon-halogen bonds on aromatic rings. We can convert or substitute the hydrogen for a nitro group, NO2. Okay? Very, very useful reaction. This requires a mixture of nitric and sulfuric acid, and the electrophile is NO2+. That one does exist in solution. Okay? So if we know how to get the electrophile, we can do this chemistry pretty easily. Why might this be a useful reaction? Have you ever heard of TNT? Trinitro toluene. So they take toluene, they put it in a mixture of nitric acid and sulfuric acid, and you can make TNT. It's a very useful explosive, right? Very powerful explosive. Okay? There are places in the United States from World War II where you can go test the soil, and it is contaminated with extremely high levels of TNT to this day. We were at war. They were making TNT for bombs, and they were not worried about the environment. When they were done with their chemistry, they threw it out the back door, almost literally. There are places where the ground is actually considered to be potentially explosive. Okay? TNT being an aromatic compound, kind of stable to normal degradation processes. Okay? And so it's hung around for a long time. It turns out if you look at the number of carbons, nitrogens, oxygens, and hydrogens, it almost perfectly balances to things like water, nitrogen gas, and carbon dioxide. So it's got everything it needs to decompose into those really stable molecules that are gases that expand, right? Yeah, and so it's called the atom balance. So people who work in explosives deal with that. We can also replace the hydrogen with an SO3 group, and we call these sulfonic acids. This is actually useful in the soap and laundry detergent industry, because it turns out that these things are used to make surfactants. Surfactants make water wetter, which means that it cleans your clothes better. Okay? And so the electrophile here is SO3H+, where the plus is on the sulfur. Notice we can also make carbon-carbon bonds. That's very useful, right? And both of these have the same name, Friedel-Crafts. Friedel-Crafts, two chemists. One is an alkylation reaction, where we are putting an alkyl group on there, like a methyl group or an ethyl group or an isopropyl group. Okay? Notice the chemistry. We need an alkyl chloride and aluminum trichloride. Aluminum trichloride is kind of nasty to work with if you've ever worked with it. But nonetheless, we form these nice carbon-carbon bonds. What kind of electrophile am I generating? A carbon electrophile, a carbocation. So what do we have to pay attention to? Rearrangements. This stuff will give me a carbocation, which is subject to rearrangement. So a lot of times you'll find that where the chlorine was isn't where the new carbon-carbon bond is going to be, because it'll rearrange. That's going to haunt you all a little bit. Okay, just to kind of tell you. Friedel-Crafts acylation also makes a carbon-carbon bond, but in this case, instead of making an alkyl group, we make a what? We make ketones. That's exactly right. So we can go from benzene rings to ketones using the Friedel-Crafts acylation reaction. Notice here we're using acid chlorides. R, C double bond O, Cl. Okay? And we're using aluminum trichloride. We generate what's called an acylium ion. Okay? The carbon is a carbocation in a way, but actually the carbon on the acylium ion is not positively charged. This is kind of a misnomer. Think about that over the weekend. I want you to draw resonance structures for the acylium ion. So imagine removing the chlorine and putting a carbocation on this carbon. It's not going to be the main contributor of that particular structure, but we'll go through that. I want to talk a little bit about the general reaction mechanism, because it doesn't matter what electrophile we need. The general mechanism is the same. So let's suppose Aubrey comes into the lab and he wants to do an electrophilic aromatic substitution reaction. So he's going to start off with benzene and some electrophile. So he's going to have something like E plus, X minus in solution. X just being a counterion. The first step is the pi bond reacts with the electrophile. And we form a carbon electrophile bond. What can you tell me about that carbocation? Is it stable or unstable? It's relatively stable because why? Conjugation and resonance. But it's still higher in energy than the starting aromatic ring. Why? There's two reasons. Number one, it's not aromatic. And number two, it doesn't have an octet. Right? So what can happen? How can I get my octet back? Do I add X minus? If I add X minus, I've just done an addition of EX across the carbon-carbon double bond. How do I do that? How do I get the double bond back? I take the hydrogen away. And that's how we get rid of the hydrogen. And now, this is now what? Aromatic. Start with an aromatic compound, I end with an aromatic compound. Nature is as it should be. Okay? But we can do electrophilic aromatic substitution reactions. That's the general mechanism. It doesn't get any easier than this. Yeah?
Since it is in equilibrium, does it lie to the left since it's more aromatic and more stable?
This one?
Yeah.
Yeah, it would lie to the left here, but what happens here is this is not a reversible reaction.
So when it does happen, it just goes.
Yeah, so this is the driving force here. This goes back and forth, absolutely. But here, yeah, a little different. All right, I've got your Chapter 12 inverted lecture and your bonus quiz. I'm going to hand those back. If you got a check mark on your bonus quiz, you got all 10 points.